Symmetry appears often in mathematics, and usually it helps to more efficiently solve a problem. And certainly that's the case with integration. So let's look at the problem that we did in the fundamental theorem of calculus video, where we had just a simple parabola that was centered about 0. So we were looking at -2 to 2. And if you notice that you have symmetry about the y-axis here. So the area from 0 to 2 is exactly the same area from -2 to 0. So we could have just simply rewritten this integral as 2 times 0 to 2 x squared minus 4 dx. Now, why did that become a simpler problem? When you have a lower limit of integration that is 0, often things simplify quite a bit. You don't have to worry about signs, you're less prone for error, so it's just a much more efficient way of solving the problem. But there's some key things that you need to recognize first and make sure you adhere to the rules before you use it. So let's get into that first. We're going to look at what kind of symmetry odd and even functions have. We're going to do a review of that, and then we'll get into actually solving a few integrals using symmetry to help us. So we'll review odd and even functions, and we know that an even function, let me grab a different color here, an even function, which is what we were working with above here, has symmetry about the y-axis. Symmetry about the y-axis. And how do we test that? Well, when we substitute in the opposite x value, we get the same y value out. So f of negative x equals f of x. When negative x is substituted into the function, you get the same exact y out. And when that occurs, you get the same y value. That tells you that it's an even function. Right, so the same y value is obtained. So an example of what we just saw here with the function above, we had the function x squared minus 4. And if I put in, let's put in 1. If I put in 1, I get 1 squared minus 4, which was -3. And if I put in -1, I also get -3. Right? So it doesn't matter whether you put the negative value in or the positive value, you get the same y value out. So that tells you that this is an even function. Now, another example of an even function would be a trig function, specifically cosine. So another example of an even function is the cosine function. Right? Because with the cosine function, if you were to fold along the y-axis here, the area to one side would equal the area to the other side. So that tells you that you have symmetry about the y-axis, and this is indeed an even function. So the trig function cosine is an even function. And in fact, any even power of x, right, where n, should have gone off yellow, where n is even, will result in an even function. So that's a quick check and some helpful hints. However, the real check is when you substitute in the negative x, you get the same y out. So that's an algebraic check for even functions. All right. So how about odd functions? What can we do there? And then I'll give you a theorem to wrap up this discussion. So an odd function has symmetry about the origin. So if you were to fold along the x and then along the y, you would have graphs that lie on top of one another. So what is the characteristic algebraically of an odd function? When you put in negative x into f of x, you get out the opposite y. So let me say that in words. When negative x is substituted into the function f of x, the result is the opposite value, the opposite y value. So an example is any power of x where n is odd. And if we were in class, I'd be asking you, what trig function do you think is odd? And you should think about the graphs of the basic trig functions. And hopefully someone would recognize that sine of x is odd. Well, let's look at the graph of sine of x and think about that for a moment. Right, we know that sine of x looks like that, right? And if we were to fold along the y and then along the x, you would get everything on top of one another, right? The pictures would lie on top of one another. So therefore, sine is an odd function. But again, the true test is whether it holds the algebraic relationship. All right. Something you should also know is that constants are even. Constants are even. Constants are even functions. And you can think about that for a moment. If I had the function y is equal to 3, and that would be up here, so let me extend this graph a little bit. And if you had that function y is equal to 3, if you were to fold that along the y-axis, the left-hand side would fall on the right-hand side. So constants are even. Now we're going to connect centered about the origin. How can we connect centered about the origin, even and odd functions, and integration? And that's when we're going to come up with this theorem. There's a formal theorem for us. And the theorem states, and again, this is sort of abbreviated language. There's much more formal language than what I'm giving you. But if a function is even, then we have the integral, and it must be centered about 0. Okay, centered about 0 says you must be going from negative a to a. All right, that's a typical mistake. You have to check that first. If that is in place and this function is even, then the integral is the equivalent of, that should have been an a, not a 2, 2 times the integral from 0 to a f of x dx. And it's much easier calculations with the lower limit of integration equal to 0, right? Things get messy when you have negative numbers. If the function is odd, then let's think about the sine function for a minute. If I was, suppose I was integrating from, let me find a different color here. Actually, purple works well. Suppose I was integrating from minus pi over 2 to pi over 2. What you should notice here is that we have symmetry about the origin, so the area above the x-axis is going to cancel out the area below. So the actual net area would be 0, and that's the second part of this theorem. If the function is an odd function, then what we have, as long as we're centered about 0, going from minus a to a, then that integral is equal to 0. And that really is powerful. So that is all I have for this. We're going to be, I may do an algebraic review just to make sure you understand how to check for symmetry in another video. And then we'll do some problems also. Maybe in that video we'll do 1 or 2. And then the rest of the class will be flipped.